Okay, so our next talk is by Pierre Vandergheynst. He is from EPFL. He's an associate professor there. He got his most of his education in Belgium, including his PhD. So, among other things, he was an editor of the Signal Processing magazine. He's currently an associate editor of IEEE Transactions on Signal Processing. So.
Okay, so thanks a lot for the organizers of what is shaping up to be a very interesting week. So Ingrid just recalled the importance of wavelets in compression and in various applications in the last maybe 2 decades. And so I'm going to also talk about wavelets, but maybe wavelets for different types of applications. So wavelets have been generating sparsity for signals and images, but I'm interested in applications where signals are not defined as functions of the real line or functions of a 2D variable, but maybe more applications like these ones where you may have sensor networks or a graph in general. So look at the first example over there. This is a map of the power grid of the US, right? And the same example could be carried out in Europe. There's tremendous problems in front of us trying to understand how we are going to disseminate electrical power when we are going to switch to distributed sources. So there's a lot of interest for people like you trying to understand in the future how we can process signals like, you have sensor networks there, you're trying to evaluate the load of the network, you're trying to detect faults in the network and understand how they propagate over the network. But you see that this network has a very strange and complicated topology. Another type of application would be if you consider the brain there. So your brain is a big network as well. This has been studied extensively over the last decade. And you could map the cortical connections in the brain. At each of these vertices, which are regions over your cortex, you could have experiments from fMRI giving you data, and you would like to process that. So you have something which is not an image or a signal, but something which is more of a network. And obviously as well, in social networks, you have users, they are sending out data, and you may want to understand, okay, if you're a company, what they are doing right now, or what they might be doing in the future, or what kind of information you would like to send them. So the point here is that you have a lot of situations where signals are defined on complicated topologies, which are well encompassed by a graph. And my idea here is just to talk a little bit about how you can, so let me just switch now, how you can maybe construct wavelets on graphs. I'll give you a very quick summary of one such construction. There are many constructions of wavelets on graphs, and I have no claim that this one is any better than the other. It's just the one I understand. And it has the features that Ingrid just reminded us about. It's a multi-scale construction, and we'll see that it's based on the idea of filtering on graphs. So that's interesting. And then the thing I really want to do today is try to see can we recycle another ingredient coming from wavelets, which is more the idea of pyramidal algorithms and filter banks, which is one of the key successes of wavelets as well. And so I will summon an old friend of ours, which is the Laplacian pyramid, which I will try to turn as a tool for computational analysis of signal on graphs, and then I will see if we can do steps towards actually having 2 channels critically sampled, filter banks on graphs. So let's get started with what kind of graph I will consider in this talk. So the graph I will always work with today will be weighted, possibly, undirected. E is the edge set and V is the vertex set. And the Laplacian matrix of the graph, or the Laplacian operator, will play a fundamental role. So the Laplacian operator is just a matrix, which is the difference between the valence matrix, if I should say so, and A, the adjacency. The adjacency simply summarizes the connections between the vertices in the graph and the weights on the connections if there is some. And D is simply the sum of all the incoming edge weights at each of the vertices. So this matrix is a symmetric positive definite matrix. It's got an eigen decompositions, which we are going to use. And in fact, it deserves the name Laplacian for various reasons, one of which being that if your graph is just a simple line graph or a 2D lattice, you can easily see that this definition of the Laplacian will be in exact correspondence with the second order discrete difference approximation to the usual Laplace-Beltrami operator. And this even carries on to manifolds. Okay, so when we do wavelets, we need to dilate something. on a graph it's difficult to dilate something. So what you do when you construct these spectrograph wavelets is that the role of dilations is actually mapped to the Fourier domain. So the Fourier domain for me will be the eigendomain of the Laplacian matrix. And if you remember what you do with the traditional wavelets, dilating them in the space domain means you dilate them in the converse way in the Fourier domain. And this is the equation that is there. Right? I will have an operator, which is this T, which acts as a Fourier multiplier. So it will multiply the Fourier expansion of functions on graph and will reshape them. And I can dilate this Fourier multiplier because it's a function. It's a function of the Laplacian operator, so it's an operator-valued function, but I can always dilate its argument. And using that operator, if I apply it to a Kronecker delta at any vertex of the graph, it's like I'm looking at its impulse response, the object it spits out, which is parameterized by scale and the vertex at which I apply it, I will call a wavelet. Right? Now I have to convince you very quickly that this deserves the name. And once I have these object wavelets, I can take any function on the graph and then project them on this set of wavelets. Now, if you use the eigendecomposition on the graph, with the phi L's being the eigenvectors and the lambda L being the eigenvalues of L, you can write down the closed form expression for these wavelets, and you can see that the sum mimics the relationship you have in a traditional case by writing down the translated and dilated wavelet as an inverse Fourier transform of itself. And you see that dilation is really as well obtained by dilating in the Fourier domain. Localizing the function is played by multiplying in the Fourier domain by a complex exponential in the traditional case. It's multiplying by an eigenvector of the Laplacian in this case. And the rest is just an inverse Fourier transform on the graph, which is simply saying I take the eigen coefficients and I map them back in the vertex domain. Okay? So you can formally now project any signal on this set of wavelets, and you can then wonder, can I reconstruct any signal from that? You can do so if and only if G satisfies such a technical condition, which is an admissibility condition. I'm not even going to bother you with the condition, but it's nice to at least remind that this condition tells you that G must be oscillating. So in order for this object to be invertible, G must be a zero mean function on the set of vertices. And so it deserves, at least partially, the name wavelet. You can build frames with these functions by simply looking at the kind of conditions you need on the generator G such that you have frame bounds. And here I have used a sort of a generalized condition where I introduced a scaling function. So all the low frequencies are taken care of by the kernel H, whereas the G are scaled wavelet kernels, just like in the classical case. The set of scales Ts you use is just up to you to choose. You could discretize T by powers of 2 as you do in the traditional case, or you may want to discretize the scale such that you have some sort of a uniform partition of the spectrum in any sense. And there's a simple way to generate frame. That's the condition down there, which dates back to, I guess, old papers by Bruno Torresani, maybe. When you have a continuous wavelet, you can just agglomerate them using this integral there. And if you do so in that way, you automatically get a tight frame. So the summary is that you have something which sort of look like wavelets. We'll see some examples. You can get frames, and you can get tight frames very easily. It's not finished. The scaling I just constructed does act like you would like it to act. That is, it can zoom in on a localized portion of the graph. So instead of maybe giving a theorem, it's better to show illustration. So here is the Swiss roll data set. It's a very famous data set in computer science. The red dot over there indicates where I'm going to actually put a wavelet. And you can see here 3 different wavelets at 3 different scales. So the first one is at large scale. And then as you put down the scale t towards 0, the wavelet is going to shrink to almost being supported only on a vertex. The theorem behind it tells you that if the generator G is actually a good wavelet generator, as t goes to 0, all the wavelets will more and more condensate into a geodesic ball of a small size. So that scaling really operates like some sort of a dilation operator. And you can then show nice and fancy examples. Here is an example coming from neuroscience, where you have the cortical connectivity of the brain has been computed using diffusion MRI. Now from that graph, we construct the graph wavelets. And here the neuroscientists highlighted one region on the cortex, and you are going to see a wavelet constructed on that graph at different scales and located at that region. At the beginning, it's a fairly concentrated object on the cortex around that region, and as I increase the scale, it's going to diffuse over the cortex more and more. And you can see at this point, it diffuses not geographically because, I guess in that particular example, the frontal part of the brain was connected to the rear part of the brain, and so the wavelet can diffuse to areas which are not local in the surface of the brain, but which are local in the topology of the cortical connections. Okay, and that's what you get when you're at very large scales. There's also a nice connections with sparsity as well. So it's easy to prove that if you have a very smooth function over the vertices of a graph, that definition of a wavelet transform will generate sparsity in the sense that most of the coefficients will be very small. The coefficients will decay very quickly as the scale goes to 0. And that is also the case if your function is piecewise smooth, although this is much more complicated to prove. Here is a simple example. You have a graph over there, which is, I guess, the state of Minnesota, and the vertices are roads or particular spots in the state. I just overlay the function which is +1 -1 over the graph with a nice cut in the middle. And what you see is the wavelet decomposition of that function. So on the top left, you have the scaling function approximation. So it's a low frequency approximation of that. And the rest are wavelet subbands. And you see the effect you expect to see is that most of the coefficients in the wavelet subbands are actually 0, and they condensate very nicely on the cut. So just like traditional wavelets, we locate discontinuities over a signal or an image. This kind of object will locate discontinuities over the graph. There's something I should point out here is that sparsity has to be understood with a big bracket around it because the transform I'm just describing is very redundant. There's no downsampling in this transform, so each of these subbands have the same number of vertices or the same number of coefficients as the number of vertices in a traditional data set. So if your graph is big, you're actually blowing up the dimension of the graph here. There's another problem with that is that if you would like to do L1 optimization for sparsity with this object, the low frequency subband is not sparse. It should be excluded from your optimization. Most of the people don't do that with traditional wavelet expansions because in wavelet orthobasis, the low frequency subband is usually very small and you don't care if it's not sparse. But in this case, you have to care because it's not sparse at all. So that's the first problem we'll have to solve later on. Just a remark on how you implement this thing. You really don't want to compute the eigen decomposition of the Laplacian if the Laplacian is big. So what you do, that's one of my notes there. I guess several of them will show up. So I can now read them, that's cool. So instead of doing that, what you will do is bring up an old trick from numerical analysis. So here is the GT of omega. You can forget the T. If you have any Fourier multiplier G of omega that you would like to use, what you will do is approximate it by a polynomial expansion, right? And if you look at that, since G acts on the spectrum of the graph, the polynomial expansion becomes a polynomial in the Laplacian matrix. So applying your Fourier multiplier is now applying powers of your Laplacian. If your Laplacian matrix is very sparse, applying these powers is very efficient. Plus, you can go a little bit further than that. If you choose well your polynomials, so a good choice, for example, are Chebyshev polynomials for which you have very good sup norm control, but also recurrence relations. So here's an example. If you want to approximate your wavelet operator by a polynomial of the Laplacian, if you do so by approximating G with Chebyshev polynomials, you can also use these these recurrence relationships between order k minus 1, and order k minus 2 to boost the computations. Right? So you never compute the eigen decomposition of the graph. You just need a crude estimate of the spectral radius, and then you use these kind of decompositions. And if you look at the computational complexity of that algorithm, it basically scales like the number of edges in your graph. So it can be quite efficient. And then if you also want to do L1 optimization with this type of wavelet expansions, you need a similar relationship for the adjoint, but the good news is that the same algorithm is being used for the adjoint. So it's a fairly efficient algorithm. You can download all the necessary toolbox at this website, and you can use that algorithm. It would still work if your data set is of the size 10 to hundreds of thousands. We haven't used it for a larger data set, but for that kind of size, it's okay. Okay. So that was a quick summary of one possible construction of graph wavelets, but it has pitfalls. Some of the pitfalls I would like to try to solve in the remaining part of the talk is the problem with redundancy. So it's a very redundant transform, which could be nice if you do analysis, but it's not nice if you do, what many people do in the room, that is optimize the representation for sparsity. So can we remove the redundancy easily? That's the first question. And the second question is, can we go on to faster algorithms? What do I mean by faster? If you look at the traditional way to implement wavelets, you would use filter banks. And the very interesting things with these filter bank implementation is that whatever the scale of the wavelets you are trying to compute, you always use the same filter. So you always do the same computations. With what I just presented, the large-scale wavelets, you will need polynomial approximation of higher order to get a good approximation of the kernel, which means you will use Laplacian powers of higher order to implement your scheme. And so the computational complexity will increase with the scale. And that's basically normal if you think of it, because you're trying to implement an object which is of big scale over the graph. So you need to do more computations. This doesn't happen if you use filter bank. So scaling is implemented by downsampling of your data, and then the projections are implemented by using always the same filter. So the computations are of the same, whatever the scale. In fact, they drop down with scale because your dimensionality reduces with downsampling. So that's really something we would like to try to do here with functions defined on graph and solve both problems at the same time. So let's have a first look at how we could do that. One important thing is that you need to be able to downsample your graph. So there's been a lot of work in computer science in particular on ways to reduce a graph, downsampling a graph. This ties back to coloring problems on the graph or the max cut problem, for example. In this case, what I would like to do is have a link with the spectral properties of the object, because everything I have defined, filtering, for example, is defined through the Fourier representation, through the eigendecomposition of the Laplacian. So I would like to have something that I can link with filtering. So if you look at what you do in the traditional case, this thing will be a data set defined on the line. You would take 1 point out of 2 and filter, right? And critically sampled filter banks would be essentially using this primitive and then do that for a low-pass filter and for an high-pass filter. And then with good conditions on the filter banks, then you can reconstruct with a simple algorithm, and that's super fast. Complexity is linear. So how can we do that on a graph and still having links to the harmonic analysis and to the Fourier expansion? So subsampling has to be done in such a way that the cosets, so even and odd in this case, would be meaningful. We should be able to do it in a very efficient way. And if possible, we have to be able to define a new graph on the reduced set of vertices. So these are the questions we have to answer. So let's go back to the traditional case. So on the line, you can see downsampling in a very simple way in the Fourier domain, right? You can simply multiply your function fi by 1 plus the higher frequency cosine, and that function is simply 1 and 0. Right? It's the fastest oscillation. It's 1 and 0, and so it selects 1 point out of 2 for you. Right? So why not try to do the same thing on a graph? So if cos is an eigenfunction of the Laplacian on the line, why not try to use the same kind of idea to actually tag vertices on the graph so that we can remove them? Okay. It turns out this is a known topic in graph theory, which connects to an old question in physics, namely nodal domains. So what's a nodal domain? Suppose you give me a signed function on the set of vertices. And a nodal domain will be defined as a maximally connected subgraph, such that all the vertices on that subgraph, the original function on those vertices have the same sign. So if you look at the polarity of the function on this set of vertices, it should be the same, right? So if your function is as plus minus, it splits the graph in 2 parts. So what we would like to do, if we look at that definition, is to find a very large number of nodal domains. So we want to find a control function such that its polarity is such that we can have guarantees, some sort of guarantees, or at least intuition, that the number of nodal domains will be very large. If possible, the cardinality of the vertex set, meaning that every vertex will be a single nodal domain, if you wish. It turns out that the nodal domains of the Laplacian eigenvectors are very special and have been very well studied. And in particular, there's this very cute theorem which tells you when it is possible to have the maximal number of nodal domains. And unsurprisingly, this happens, or this is controlled in the case where you're looking at the eigenvector connected to the largest eigenvalue, just like in the case of the grid or the traditional data on the line. But the theorem also tells you something which is really sad. So let's look at it. It says that the number of nodal domains associated to the largest Laplacian eigenvector of a connected graph is maximal. Maximal meaning that you can reach the upper bound. The number of nodal domains is the cardinality of the vertex set. But if and only if you are in a very restricted case, which is when the graph is bipartite, right? And that's interesting, but that's also sad, because if you know in advance that your graph is bipartite, you don't have to worry about downsampling your graph because it's defined as two cosets, right? So there is a very natural way of downsampling it from scratch, right? And in general, you have theorems that tell you that the number of nodal domains, nu of G, are indeed connected to two coloring by this equation. So the maximum number of nodal domains is the cardinality of the vertex set minus the chromatic number of the graph plus 2. And so from this equation, you see the two extreme cases, the bipartite case on one hand, where you can have the maximal number of nodal domains, and the complete graph on the other end, where, well, you have to use a different color for each vertex. So it may be like a blocking situation, but nevertheless, we'll try to use this idea. So we'll try to get back to our intuition that Laplacian eigenvectors, just like on the real line, are objects which are oscillating over the whole vertex set. And as I ramp up in the order of the eigenvalue, the oscillations increase. They are faster and faster. So I will define these objects. So I'll split my vertex set using the polarity of the largest eigenvector of the largest eigenvalue. And I can define these masks precisely like it was done on the traditional Euclidean case. So there's a mask which selects those positive vertices and another mask which selects the negative vertices. For very simple graphs, it does what you hope it would do. So for the line graph, it's just downsampling. For the ring graph, it's just downsampling. For the lattice, it's just quincunx downsampling, which is kind of interesting as well. Now, unfortunately, again, there are agonizing limits to what intuition can buy you. One of the problems with this strategy is the multiplicity of the largest eigenvalue. So if the largest eigenvalue has multiple eigenvectors, how do you choose your control eigenvector? Or even worse, how do you choose a vector in that subspace? You at least need a prescription. Even if you have a prescription, it could be numerically ill-defined. And so every time you run your algorithm, you might end up selecting a different control function. And there's also the problems with the graph, which have very flat spectrum, right? So close to the spectral radius, all eigenvalues are very close, and so it's getting very difficult to distinguish them. Moreover, there's another problem, is that the Laplacian eigenvectors do not always behave like you would have the intuition they do. In particular, it seems to be true that for random perturbations of simple grids, the Laplacian eigenvectors are not delocalized, but localized. I couldn't find a precise result about that, but I found something even worse, is that this seems to be true for even simple trees. And that has been brought to attention by Saito this year. So even for some trees, from a simple class of trees, the Laplacian eigenvector will be very localized, even when you go to higher eigenvalues. I will nevertheless ignore these two facts and carry on with the algorithm and show that you can use it in practice, but you have to remember these limits. So let's go to a pyramidal algorithm, which has a filter bank implementation. It's an old friend of ours. It's called the Laplacian pyramid. In the Laplacian pyramid, you take your data, you run it